Okay, so I hope you could recover a bit, and welcome back to the neural network and deep learning lecture. And so also in this lecture, after the break, we'll start a bit with a new topic. So far, we have looked into different types of architectures. We did learn the different core components of a lot of neural networks that were RNNs, TDNNs, CNNs, self-attention parts, and then the state space models. And then in the end, we also looked a bit how to combine them in different types of higher structures like decoders, encoders, and so on. And so this first part of the lecture was a bit about what type of components you can use in order to build strong state-of-the-art neural networks. Based on that, we want to now look in the next few lectures on how we can then train these types of models efficiently. Today, we'll look into the basic training, how we can train these models. I mean, you have a basic idea, hopefully. If you remember, in the very first lecture in the introduction, we explained the basic backpropagation algorithm. But we'll see today there are several challenges with this, which should be addressed, how to update, when to update, and things like that. And then we'll continue with more advanced things. Like next week, we'll look into how we can specifically address very deep networks that they're still good to train. Then we'll look into other types of learning, transfer learning, self-supervised learning, and so on. So with this, we will try to start and look what we are currently having from network architecture, and then how we can train them. So the networks we have seen so far are typically will have some multiple layers, and that can be normal feed-forward layers, that can be self-attention layers, and all the others. And last time we explained also briefly this transformer architecture where we, for example, mix things, where you have a self-attention layer, and then typically on top of that, you have the normal feed-forward layer, which is just like put at every position. In generally, we have these types of multiple layers, where we put our input here in green at the bottom, then we calculate all the hidden states. The hidden representation of one layer is then always the input to the next layer. So these hidden representations go up until we are there on the top, where we have then our output, which is then depending on what we're doing, whether we're doing a classification task, whether we are doing a regression task, or anything like that. And in general, these layers look like that. So we always calculate the new hidden value hi of the ith layer by some function which depends on the input, which is the hidden state from the previous one, and of course on the parameters. And typically the parameters are dependent on the layer. So each layer has its own parameter. If you have two LSTMs, they have different parameters if you have a CNN and a LSTM or so. There is some work also like, can you share the parameters so that you mainly do the same operation over and over again on the same input? But this is not the typical thing. What we are then having as our HI is either a vector, or we have seen structures of vectors. So typically what we have mainly were sequences of vectors. You can have also 2D structures. We had at the beginning for images, or if you think about graph neural networks, it's more complex, a graph structure, which does that. But you can view HI always as either a vector or some structure of the vector. When we are doing then our function is then this function which transforms our input to the output. The important thing we already pointed out at the beginning is that this function needs to be differentiable, and the differentiable needs to be helpful, because that is what we're today looking into. That is, then we can do efficient training. And the most simple example for that would be a multi-layer perceptron, or like We're like a single layer of that, where what we're doing is just a linear transformation. So we take our hidden representation hi minus 1, we multiply it with our weight matrix AI, then we get a new hidden representation. Then we need to do one nonlinearity in there, and that is then our new hidden representation. And at the very beginning, we motivated this type of nonlinearity because if we would just do several linear operations, these can all be represented as one single linear representation. So we wouldn't really gain anything from having multiple layers. And yeah, this is the basic type of structure we will today look into, and based on that, which look into how to train. And of course, the F doesn't need to be a feed-forward neural network. It can also be a CNN, it can be an LSTM, and so on. Then you just have a different type of parameterization, how you calculate that. When we're doing training, the aim is, so what we're today want to look into when we're training is the target that we're having is to find these tethers. So our weights that enable us to then calculate the forward pass. And these number of parameters are very high. I guess you all heard about large language models where they're talking about like billions of parameters, which makes it clear that it's not somehow a good way to like manually select them, to somehow guess them, but we need some good way of finding them. And how that is done with a supervised training. That means the idea is that we compare the solution by the network to a solution that we know is correct. So that you see here in blue, we have the solution of the network. We are comparing it to a solution of the reference solution, and then we are calculating some type of loss. So that is another component that we have. We need to evaluate how good is the solution we're having compared to the reference solution. And then we're doing this typically not by one example, but we're doing it over all our training examples. So you see here, the overall evaluation is then that we sum over all our training examples, xi and yi, and we are then summing up the loss, which is calculated between oi, which is the output. COI is calculated by taking the network and inputting the input there, and comparing our output to our ye, so the output. So in this case, you see that each example is treated the same way. So again, this is somehow what is the easiest thing, because we don't have to think about. It might be in some cases that you are more relying on some examples and less on others. You can also start to add their weights in there, but the default easy solution is to just say every example has the same importance, and we're doing just the average over all our examples. And so this is somehow the training, and that we want to look more into detail. Now we are saying already, so we can calculate directly OI and do that. So the first question is, how can we already predict a solution at the beginning where we don't have any parameters? So how is this normally done? Any idea? So the network,
Find the format of the solution with the neural network design, and then we have an arbitrary bad solution.
Yeah, but what do you take as theta? So how do you define your theta? So which could be, for example, your matrix at the beginning.
Just randomly initialize.
Yes, so that is the important thing. So we can do some direct calculation by just doing some random numbers. Of course, this will be very bad, but it is possible to do that, and you can generate one output, which is important because then you can start. Now we see how we're doing our training. We can directly start with something and then try to improve it. This random guessing is a bit more difficult than thought. So it's not best to just take any random numbers, but to think about a bit like that you get decent random numbers in there. Can somebody estimate what might be good properties of this random initialization? So we already said we are doing gradient descent. So then, of course, it's somehow important that you have random initializations where your gradient is somehow good so that you can really train. If you would start in a situation where the gradient is very small, so you only do very small updates, you can't get out of this bad solution. So therefore, there is some work on, and we'll have a look at that next week, on what is like decent numbers to start your initial number. So it's not best to take any numbers, but to rely on best practices there and to initialize your network in a way that you get a good starting point for your thing. So what the training then is what we're doing, we're trying to optimize. So there's a whole training process. It's just an optimization problem where we try to minimize the loss, and the loss is calculated over all the training examples. So as a minimization or an optimization problem, we try to find our weights theta, which minimize the loss of all the training examples. So we have to somehow find a good lambda, a good theta, which will exactly minimize this type of loss. And yeah, a first way of doing that might be to just do random guessing. I mean, we initialize that. We could just now continue and guess and guess and guess and always like estimate how good they are and then continue guessing. However, this is of course very inefficient, and especially since we have many different types of values, might not be the best way. So we have to somehow find a better way of somehow searching and doing the search problem to find the best ways for our thetas. And luckily, there is a very successful approach for that, which can guide us in finding good solutions. And this is called a gradient descent. And therefore, the important thing is that both our neural network and our loss function needs to be differentiable. Because if it's differentiable, we can calculate just the difference, not the difference, but the, how's it called in English? The derivative, yes, sorry, I only have the German word. So the derivative of our weight of our error with respect to the weight. You see that here for the one-dimensional case, first the easy thing. So if this would be one weight and we would only optimize that, then we can calculate for each weight. We could have this type of function that we see for different weight values, we'll have different types of errors. And the problem is now you don't know this function. So you don't know for each weight what would be the matching error. What we only can do is we can evaluate that on discrete points and look how big the error is. So we cannot just take the function and find, oh, at this position here is our best value. But what we can do is we can calculate the derivative. And then you see here, this will show you in which direction the function goes down and in which goes up. And then we can go, so it shows in the direction of going up. So we can go in the worst direction, and then we can go down. And if we're doing small steps, we would end here. So you already see a bit one big problem of this type of solution. We are not going into a global best solution, but we'll end only like in a local best solution. However, it gives us some good direction to go, and we are not doing just random guessing and have to see. But we can just follow our gradient and then would end up here to have maybe a decent, good solution. Where in which case would we find a global optimal solution? So there is this set of convex functions. So if our function would be convex, so for example, only from here to here, then we would end in a global best solution. However, since it's an interesting problem, it's sadly not the case. So typically a neural network is not. We won't find the globally best solution. However, if we're doing gradient descent and doing decent decent hyperparameters, we often end in a good solution. And we'll see even sometimes it's even better to not end up in the best solution, but only in a decent solution. Does anybody have an idea why? Yes?
Because it's only the best solution for your training data, thus the best solution for the real data might be different.
Yes, exactly. So we are only optimizing the loss on the training data, but this is not what you're really interested in. I mean, you would be really interested in how good it is to be on some unknown data. And then it might be that you like do wrong training, we'll come to that, like overfitting, so that you end up in a solution which is good for this type of data, but it doesn't generalize. So the additional challenge is that we're optimizing a function, but we are not really interested in the performance of this function, but we are more interested in how good does it generalize and on a similar function. Okay, so this is the most simple way of putting it. So that would be the one dimensional. We can also have a look at it a bit more in a two-dimensional space. It's already getting difficult. So we have weight 1 and weight 2 here. And then the green point is maybe where we are. And then I try to model there where it's like there is a minimum with lines, and then again the gradient which show us where to go, and we could go there. But in reality, of course, it's a lot more complicated. We're not in two-dimensional space, but in number of parameters, so in millions or billions. Visualizing that gets a bit difficult to do that. So this is our overall aim. We want to somehow minimize our error function. And now we can go it step by step. We'll first look at how this gradient descent in generally works. And then in this way, look at each of the problems where there are specific challenges that we somehow need to address. So how do we do that? The first thing we're doing is we have to calculate our forward pass. So we take our randomly initialized model, we are taking some example here, and then we are calculating based on our function, we can calculate all the hidden values. So we can go step by step, take this one, take the first function, and then calculate h1. And then based on h1, we can calculate h2. Based on h2, we can calculate h3, and so on until we have calculated our output. So this is what we'll refer to as the forward pass, and that is the first step in the training. This forward pass, that is the important point here. The forward pass you're doing in both. So you're doing it in the training, but you're also doing it in inference, because then you're done. In inference, you're at this point done. In training, we only have done the first step and now have to continue. The next step is then we have to calculate our loss. So we have to measure somehow how good is our prediction compared to the reference prediction that we're having. And this is now there. It depends a bit on like what type of network do you have. So depending like on what do you need to predict, it might be different, or like there might be different ways of measuring the error that you're doing. The most typical one, or the most first feed forward, is what is referred to as a mean square error loss, where the idea is that we're exactly doing what the name says. We're calculating the mean square error between our network output O and our ground truth Y. And you do that just if these both are examples, you do that directly. If it's a vector, you can also calculate that. And this is typically done if we're having regression. So if you have to predict some real value, then it makes sense, because if you're predicting a real value, it's somehow that the nearer you are there, the more helpful or better it is to calculate that. So this is, yeah, in this case, the typical thing. However, there's a lot of neural networks which are not used for a regression model, but what we're trying to do is some type of classification. So we had that also in a lot of examples. You want to somehow predict 1 out of n, 1 of 2, or 1 out of n classes. And especially in these types of problems, we are typically using a different type of loss function. So before we're going on with training, since this is an important component, we want to look at the most important type of loss functions that we're doing there. The first typical example is the thing where you have a binary classification problem. So your YE is like a binary label which says is this class 1 or if it is class 0. And if you train it, you typically interpret it this way, so that the probability OE is a probability, the output OE is a probability that the label is 1. And if you then want to have the probability that the label is 0, it's 1 minus the output. So that's the typical thing of how to interpret the output. So if you're doing that somehow in the space again, you're trying to have separate the positive and negative examples, and the distance there to this threshold, to the 0.5 threshold, is showing you whether this should be is more probable of label 1 or if it's probable of label 2. And if you're doing it in this type of way, you can think of that. I mean, a lot of machine learning problems, what you want to maximize is the probability of your training data. And in this case, it's often you're not directly optimizing the probability, but you're optimizing the neck-lock probability. So here we have, you see, the probability of YE given xi, and then you're having the logarithm of the probability, and then the minus sign. And you're just doing here the sum of all the examples, and then you're doing the average. So what you're trying to do is that you're optimizing the neck-lock probability of your thing. If you want to optimize this one, you can now put in here the probability definition we had before, which would mean if the label is 1, the probability is OI. So YE, your label, can be either 0 or 1. We had a classification problem. So it can be 0 or 1. If it's 1, then your probability is O. So you take here, in this case, 1 times the probability. If the label is 0, then this one is 1. 1 minus 0 is 1. If the label is 1, this is 0. And then your probability is 1 minus OE. So if you take this formula in there, that's exactly what you're doing. You're just optimizing the probability up there. And depending on whether the label is 1 or 0, you have to take either the output or 1 minus the output for that. This is, of course, only makes sense if OE is really a probability. So the value should be between 0 and 1. And this is, again, then what people refer to as a binary cross entropy. So if you're trying to maximize this, you'll try to minimize here our locked probability, which is just YE ln OE plus 1 minus YE ln 1 minus OE. So again, the idea is we'll check what is our reference. If our reference is true, then we're trying to get the probability as high as possible. If it's 0, we're trying to get the probability as 0 as low as possible. And so by training this way, what you're doing in your neural network is, again, you're trying to just maximize the probability of your training data to do that. So this is, somehow the typical thing of doing it in binary classification problems. So where your output You see you have one neuron at the top, you have one neuron for your output class, and this is either 0 or 1. Then, of course, there is also the challenge. We're not always having binary classification problems. So often we have also multi-class classification problem. And in this case, we already learned how we represent the label. Is the same way as we represent our input with this type of one-hot representation. And then it was important that we represent the output of the network. We can do that using the softmax activation. So how does that work? What we want to achieve is somehow that now, if we have a multi-class problem, you have maybe 5 output classes. What you try to achieve that each of these ones correspond to the probability that the output label is exactly the class. So this is the probability that this should be reflected in the probability that the output is of class 1, that it's of class 2, this is of class 3, and this is of class 4 that you're trying to achieve. In order to achieve that, you now, of course, need an activation function which ensures this. So which ensure that this is a valid probability distribution. What are the properties that we need to fulfill? That we have valid probability distribution. Yes?
Must be between 0 and 1 and sum to 1.
Exactly. So this we have to somehow achieve. And if we just use any random activation function, that doesn't work. However, there's the nice softmax activation function as shown here, which rescales the input to ensure that this is always exactly the case. And this is achieved by taking our input and taking it to the e to the power of the input, and then normalizing it over all possible things. If you're seeing it, e to the power of anything is always a positive value. So in the end, we will have definitely a positive value. And by normalizing this, you ensure that the sum of all are together 1, and thereby they have to be all between 0 and 1, and the sum is 1. So we are exactly achieving what we want to have. So this is like a very, very typical type of activation function. You typically have always at the top layer in order to achieve that your output is nicely interpretable as a probability distribution where you can achieve that. So if you now think about text-based models where to predict the word, what would be here your output dimension? So if you have some type of predicting the next word or something like that. Yes?
Vocabulary size?
Yes, exactly. So there would be here the vocabulary size, meaning that you need to have a quite large vocabulary. So that like output class. So you might have here 10,000 different classes. If you have some type of classification problem, you want to do an image, whether it's like in 10 different types of animals seen there, then you would have here like 10 different output classes. And then if you have these type of multi-class problem, the typical thing is not the binary cross entropy, but just the general cross entropy, sorry. As you see here, it's the general cross entropy then. It's very similar calculated except that we are not having like just 2 cases, 0 and 1, but we're having all our different labels. So how does it look like? So our reference here now is a one-hot representation. That's YE. And it has like k-dimensional, where like all values are 0 except for one single value, which is 1. Our output is this type of probability distribution where we have for each value a bit like a value saying how probable the output is. And now what we're doing is we're multiplying always like a position, like dimension-wise, the value of y with the logarithm of O. So what you're doing is you're multiplying this value with this the logarithm of this value. You're multiplying this value with the logarithm of this value, and so on. Now you can shorten this, I guess. You see all how we can. So what is the final result if we are doing that? This type of case. Yes?
That we only have one y, we only get one logarithm times the output logarithm of that class.
Yes, exactly. So what you only have to do is you select mainly the correct solution and then take the logarithm of this output. So especially like in implementation wise, to do that on a GPU, you typically don't do the metric, the multiplication of the two vectors, but you just do a select operator which selects these index and does that. So you're doing there a lot faster in calculating. One point could be that it might be, of course, this is a bit in some way bad if we first think about it. So we only give feedback to this one, and we're not giving feedback to any of these ones. So you're only saying, okay, this one should be as high as possible, but you're saying nothing else about the others, which seems to be a bit of a weak feedback signal. Do you have an idea why this is not a big problem? There you have to think about our activation function.
They have to sum it to 1, so that means have one higher value, the others get lower.
Exactly. So in order to increase this, we on the one hand have to increase the input to the activation function for that, but the other way of doing it is to decrease the values for all the others. So by this type of activation function, we are directly, if we are influencing even like giving feedback only to one dimension, we are influencing also all the other dimensions. Because in order to increase the value here, what we have to do is increase the value for this dimension and decrease the values for all the others. So we are not only giving feedback to one dimension, but we are thereby spreading the feedback overall and giving feedback to all the other dimensions also. Okay, so then we have calculated the loss, and then we can do now the next step, and that means we can calculate then the backpropagation. So what we have to calculate is the derivation of the neural network input and YE, and then the loss of that with respect to the parameters that we are having. And therefore, we can use again the rules of derivation, and that is the loss derivated to the neural network output times the derivation of the neural network output to our parameters. And now we can do that from top to bottom layer-wise. And in each layer, we have to, on the one hand, calculate the loss of this hidden activation, so of the output, with respect to the parameters in this layer, because that is the derivation of the function here with the respect of the parameters, because then we can calculate the overall loss or the overall change we have to do on the parameters based on the loss that we have calculated until here, or the derivation times the value we are calculating here. And then we can here update our weights or know at least in which direction we have to go. How we update our weights, we do then in the next step. So this is the one thing you have to calculate in each layer, but that's not all. You also have to pass the error further down. So you also calculate the derivation of the current hidden state based on the previous hidden state, which can be calculated similarly. And this is then important for the updates in the lower layers, because the updates in the lower layers, you have the derivation up to this layer times the derivation from this layer to the next layer times the derivation of the next layer given its parameters. So by calculating these two derivations in each step, you can then like propagate your error all the time and calculate all these types of errors. Does that somehow remind you of something if you look at this, like calculating the backprop from top to bottom? We had very similar formulas already. maybe you can remember on the recurrent neural network, there is something very similar happen. There it just doesn't go, the error doesn't go from top to bottom, but we did the error from right to left, sorry. So again, from the end, you calculate the error and have to calculate all the way. So you have to do that somehow both from the top to the bottom and from the right to the left if you have a structure. So all the way in your computation graph, you have to calculate your errors. We also looked into that when we talked about the computation graph in the GPU, where exactly this type of thing is done. And if we're doing that, we now have for all our parameters, we should have calculated the derivation of the loss, which compares the neural network output and the reference output with respect to our current parameters. So in each of the layers, we know like how much it contributed to the overall loss and in which direction the error is going for all the parameters, for the weight matrices and so on. So so then we have done our gradient calculation for one single example. What we now need to do is we said we want to minimize here over the sum of all possible examples. So somehow we need to also add up the gradients that we get from different examples. The very nice thing is that this is linear, so that's quite easy. So in order to calculate the derivation of the sum of all examples, what we can also do is just sum up all the derivations. We can change these two operators. So that means what we're doing is we're putting one example, calculating the gradient, then we're doing the next example, calculating again the gradient, and we just have to store the gradients that we have. So in principle, how that looks like, so the first thing is we're putting in one example. We have here all our parameters. We are calculating the forward pass. For the forward pass, we of course need our parameters. We are calculating then the loss on top of that. Then we are doing the back propagation. And when we're doing the back propagation, we are storing for each of the parameters, we are storing what are the gradients that we need to have for them. Then we can take another example in there. We are again doing our forward pass, calculating the new values, and then calculating our derivations. And these need to be add up to the previous ones so that we store them and accumulate them over all the steps. And yes, so then we're somehow nearly done with our gradient descent, or at least with the baseline thing of that. There's one thing missing. What do we need to do now? Once you have calculated all our gradients. Yeah. Yes, exactly. So then what we have to do is we take our previous value and say the new value of this parameter is some learning rate eta, and then the derivation which we calculate. So if we think about that, we are going a bit in the direction of the derivation, or if we're minimizing in the different direction. So if you see that here, we're calculating the derivation and then going, or the negative derivation going in this direction, then we're going a bit more, and always following the direction and always reevaluating at this point. And hopefully then we'll end up in some small value. So and this update is, the basic idea is very easy. Just take your old values, you look into which direction your gradient is showing, and then you're going in this direction, or like going in the inverse direction. That's why there's a minus, because the gradient is showing to the maximum. We're going to want to go to the minimum, so we're going in the inverse direction, and that you're doing all the time. So we have done our basic gradient descent algorithm. So what we need to have is some learning rate, not k, which is eta down there. We need initial parameters. And then while we didn't reach the stopping criteria, we go over all our examples, we calculate the gradient, we sum them up, we apply the update rule, and then we going on and on and on. So this is the very basic way of training your type of neural network. We've seen what we all have to do. So most thing we spent now is like computing the gradient. Then we looked a bit on the sum up, and then we do the basic update rule. So it seems to be solved. So we're done after half the lecture. But you can imagine things are a bit more complicated. And there is a lot of challenges. We are applying the gradient descent, which assumes and only works well if you have this type of convex function where you have one single minimum. In reality, it's not the case. It's a very chaotic loss function. So if you're doing it really bad, we'll end up typically in some type of local minimum. We also had already discussed the problem. We're optimizing our loss on the training data. Well, we're not really interested in how good we can memorize all our examples. We are more interested in like how good it can deal with new types of examples. So there are several challenges which won't be addressed by that. And therefore, we'll look today into 3 parts of this algorithm and try to discuss them a bit more. The first thing is we just put here stopping criteria. But what is the right stopping criteria? So when should we stop with training? Because of course we can't go on forever. At some point we have to say, okay, we're done with training. So we need to find somehow a decent, good type of stopping criteria. And that is the first challenge we have to address in this type of algorithm. The second thing is, now here we said the very basic first idea. We're just going over all training examples and then calculate summing up the thing. Does anybody see already what could be a problem by this? I mean, if you think about a huge training, millions of examples, that is super slow. You have to go over all your training data, then you're getting the gradient, you do a small step, as we saw, and then you have to again go over all your training data. So this is not really efficient. So we have to see about what is like a good sample size when we are doing our update. Because you see, I hope you can recognize in this pseudocode, what we're doing is we are summing up within the training examples here. And only if we're done over this iteration, we will update our weights. So this is, might not be the best. And then the last thing is, what is a good update rule? Again, because we are on quite complex territorium, the direction might sometimes change. So the question is, how large do you want to update? You want to, at some point, converge into a decent minima, but you also don't want to like just find the nearest one, which is only a very small one. So the question is, what is a really good update rule, which can achieve that you're fast getting your the best results. Good, but let's start with first with the stopping criteria. So you can, if you can monitor over the time of the iteration, you can look at your loss, your error, and since you're doing gradient descent, hopefully it will. I mean, in reality, it might not look as nice as you go. But in general, you should minimize your error, so you will go down, 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 and your training will converge to like the minimum thing of error. The problem is this is only your error on the training data, and then you can in parallel also look onto some other data. So if you look at your test data, sadly, it looks a bit different. So what you typically see is some type of this. Like both jointly go down, and you can improve your loss. So you're getting not only better on your training data, but you're also getting better on your test data. But the problem is at some point here, the test data goes up again. And this is because some of the training data is memorized. It just only knows the correct solution for your training data, and then doesn't generalize anymore as good to your other type of data. And we want to somehow prevent that. If you're just having learned by heart all the solutions, you haven't understand the topic. And then if you're getting a different problem, you cannot transfer this. So this is something we don't want to have. So we somehow have to prevent and not training till the end, till somehow our training loss is no longer improved. So of course, what would be nice is if we can just stop here. But hopefully you all know during training, you're not allowed to look at your test data. So we don't know where this is the case. I mean, it may be in some problems it's here, in another problem it's more like this shape, and we could go to here, or it already stops here. So there is no clear way of getting there. So we have to find a bit of a different solution, which hopefully you already know. How would you do that? Yes?
We could check if we could have a different test set, like separate one not included in the training. And if that test set, the error increases again, then we can stop.
Yes, exactly. So this additional test set, you have different names for that. Can be something like a validation set or development set. It's typically how it's called. And of course, it might not be a perfect approximation. I mean, if you have different sets, you're not always 100% sure that's the same, but you should define your validation set in a way that it's best approximates your test data. So typically you use the most similar data to what you expect. Again, you're not sure what you're expecting in test case, but hopefully you have some good guess of doing that. I mean, if you're testing it always on new data, then test data will be all as newer data. So it's best to take as validation the newest data that you have, if you think about that data is changing over time or things like that. And now what you can do is, you can't find the optimal spot, but you can hopefully find a good spot of the validation data and stop once you've reached a decent good value of your validation data. So what you're doing is, and what is then referred to as early stopping, is that you monitor not only your loss in the training, but from time to time after some updates. So you want to be efficient, so don't do it every time, but after a decent amount of updates, you're also always evaluating how good you're on your validation data. Then you should see that you're getting down on your validation data, and at some point you're getting up again. And if you're getting up again, this is a sign that you can stop and you're no longer training on that. And if you wouldn't do that, what is happening here on the right side is what is referred to as overfitting. So you're overfitting to your training data. You're only getting good at your training data, but you're generalizing no longer good enough. Before that, you're underfitting. Your model is not trained yet well enough, so you should continue and get better. Do you stop typically the first time you're once you're getting worse on the training, on the validation data, can you directly stop? Yes?
You don't know that you're at the lowest point, so you have to train further on. And then you will see that the error goes up, and then you will probably load an older model to use this one.
Yes, exactly. So that is what's typically done. You store always a model which has the lowest perplexity on your validation set. Here it's very nicely shown that you always have a straight line, but of course this might not be the case. It might that your validation error goes up a bit and then goes down again. So what you should do is continue a bit further till you're somehow sure that, oh, now I'm getting really bad. At this point I can stop. And then you can check which was my lowest point and take this checkpoint as your final result. Good. Any more questions to early stopping? Good. Then we can go for the next part. And we said the next part is a question about the sample size. So when should we do an update of our parameters? And maybe the first idea you can do is what is referred to as batch gradient descent. So you update after you've done one epoch. So typically with an epoch, we are saying that it's one iteration over all your training data. So you go once over all your training data, you then calculate accumulate your gradients, and then you update the one, and you're going once over all your training. The nice thing is, then of course you have a very good estimation, and you're really optimizing the function we were talking about before. So we said, if you remember here, okay, here, so we want to minimize the function up there, which is the sum of all loss. In order to do that, we can do the derivation based on the sum of all the derivations. So if we really want to optimize this loss function, what we have to do is really update only after we have seen everything. However, this is very, inefficient. And therefore, there is another way of doing it. And the other thing you can do is what is referred to as stochastic gradient descent. That is the other bit of extreme. That means, like, after each example you've seen, you're not storing the gradient, but you're directly doing your update. So if you're looking at the algorithm, what we had before is what is referred to as batch gradient descent. So we are doing all our examples. We are computing and summing up the gradients, and then we are doing we are applying it. The other thing you can do is the stochastic gradient descent. What you're doing is you sample one example. So you randomly pick one example, you compute the gradient, update your weights, and then you continue again. So you sample again, you calculate your gradients, and you update the thing again. So this, of course, is in some way very nice, because now you do a lot faster, you do a lot more updates, you a lot faster go somewhere or change your parameters, and thereby hopefully faster reach some good type of result. Does anybody see also a problem which happens in this case? Yes?
I mean, the issue is that often you go in different directions shortly after each other, and they cancel each other out. It would be more helpful to just sum them up and go in the general direction.
Yes, so you have very noisy gradients then. So you go in the one direction, then you go again in the other. So you're not, going really in a good direction, and that makes your update then again not, your training not very stable. If you go in the wrong direction a lot of times, then you're ending up there and don't get out of it. So it's not that you nicely go that, but you go somehow randomly across all directions, and that is, of course, again, not the best we want to have. So the both extreme solutions seems not to be the best, and that is why, not very surprisingly, what people are then doing is, okay, if it's not good to always update, if it's not good to only update after we've seen all the data, there might be some way in the middle so that we're updated if we have seen a decent number of updates. And this is what is referred to as the mini batch gradient descent. So you average your loss function over n samples, and then you're doing your mini batch update, which again also takes here the number of samples into account. So you're averaging your loss over the mini batch, and then you're doing the update after the mini batch. So the hope is, and that's exactly as motivated before, if you have gradients which show in different directions, it might be good that, the wisdom of the crowd, that like the average of them is a decent direction, and therefore we're averaging the gradients and then going into the direction of the average of that. So if we want to do that by the algorithm, what we have to do is, as seen here, so we always get some type of batch. So we have to select some subset of our training data. Then we are going over all the examples in the subset. We're computing the gradients, we're summing them up, and then we're doing here the update rule where we average over the gradients that we have. So then we have somehow, a decent, good, combination between stability and still some type of fast update. Of course, we have introduced some more hyperparameters and thereby also add a bit of a challenge again. So the first question is then we have to somehow find what is a really good batch size. So we don't want to make it too big because then we have very slow convergence. You also want to do it too small because if it's too small, then you have very noisy gradients and it doesn't really work. Making things even more challenging is there is not the one good solution which is always working fine. But for example, it really might depend on what type of network you have. For example, when the self-attention was introduced, it was first quite difficult to train it stable because there, like for example, the batch size that you have to have, the mini batch size, so the number of examples is significantly higher as when people were using RNNs or LSTMs. So it depends on like what are all the other configurations of your network in order to achieve there a good batch size. And so there's always a good way of making it doing these things based on best practices which are there. And even there, describing what the batch size is not as simple as you might think. So if you have a straightforward classification problem, this might be, or this is relatively easy. If you have a batch size of 5, it means that you have 5 examples. But if you now do a sequence prediction task or sequence classification task, where in one example you do like 10 predictions and you predict 10 labels, and not all sequences have the same number of labels. I mean, you have sentences which have 5 words, and you have sentences like have 10 or 100 words. Then things, of course, get more problem. Do you now count how many examples you have, which would be the easier one, but you get a lot more feedback and more updates if you have a long sequence, because remember, you're calculating your loss function at each of the positions. You always do a backpropagation, or like you backpropagate all of them. So in a long sequence, you get a lot more feedback. So maybe the gradients will be higher, and therefore you might need to average them different. So there is a bit of way to think about how to do that. And then, for example, typically, if you talk about the batch size in natural language processing, it will be the sum of the elements in all the sequences. So it's not like if you have a batch size of 10, it doesn't mean that you have like 10 examples, but it can be then only like one example with length 10. Of course, then it can't be that exactly the same anymore, because you might have like sum up to 1,225, and you don't take then partial sentences, but you should think about that, how to do that. There is an additional challenge is, of course, now we said we have to sample here. We have to, sample here, and there's different, again, hyperparameters choices which you can make. The one thing is that if you sample with replacement or you sample without replacement. I mean, more stochastic, more random. If you sample with replacement, on the other hand, that would mean that you might haven't seen some examples at all, which is then again a bit of a disadvantage. But normally both of them somehow work. You just should be clear that these are two possibilities, and you have to think about what you have to do. Which makes things even additional challenges is that we're now talking about two types of batches which are correlated, but which need not to be the same. So you especially have to think about that since we're all training things on a GPU. So there we typically have two types of batches, and they are correlated, but they don't need to be the same. So the one thing is your batch size from the optimization. That means the number of examples between updates. And there you have this type of trade-off. You want to have it as big as possible in order to have a stability, but you want to have it as small as possible in order to have it have a good convergence. Then, if you remember back at the beginning of the lecture, we talked about GPUs, and there we're also calculating not each example singularly, but we are calculating batches. So we are putting several examples together into the neural network and in parallel calculating the forward pass and the backward pass. And therefore, there we have the trade-off then between speed and memory, and we want to maybe have more examples in there. So these two batch sizes can be the same, but they don't need to be the same. The only thing, of course, is that the batch size for optimization has to be bigger than the batch size for the GPU. You cannot like update between the parallel calculations. So you always calculate all of them together, then you wait, then you can either update or you can do more. So what you have to have is something like that. The batch size for optimization is some integer number times the batch size of the GPU. And yeah, that is how you can do that. There's one additional challenge with the how you select or how you put examples into your batches. So from an optimization point of view, you want to have a good, in each batch, you want to have a good representation of the whole population. So you, of course, in one batch, there should not be only short sentences, because then you're generating a gradient, which is good how to optimize on short sentences, but you might be bad at long sentences. And so you want to have this batch for optimization as random as possible. The problem is for the batch size of the GPU, it's different. You want to have them as similar as possible, because then you can do the calculation the similar way. So if you remember, we have to, in GPUs, we have to do all the same calculations for all the inputs. So if we now have a sentence of length 2 and the other of length 100, how can we do a batch processing? Does anybody remember? I think we had that. So you have now a one sentence of length 3 and one sentence of length 5. But the calculation in the GPU always has to be the same. So how can we make the calculation of the length 2 and length 100 the same? Yes?
We have the sequence.
Yes, so we have to pad the sequence and later ignore this type of calculations in there. So then we are mainly doing two calculations, which are both of length 100, but the 98 calculations that we have done for the 2, we throw away. There you already see that this is not really efficient. To be very efficient, what you want to have is that the lengths are as similar as possible, because if the lengths are as similar as possible, then you throw away the fewest. So you want to have that the sentences are maybe all by 89 or 99, then the calculation is very simple. And now you see the problem or the trade-off you have within your GPU batch. You want to have as similar sentences as possible, while for the other one, you want to have as far, like as distant as possible. One typical example is that you exactly do that. So you sort your sentences, your example, put similar ones into your GPU batch. If you then do several GPU batch, you randomly pick them and thereby have a distribution. But that all has to be kept into mind, because if you're doing it a bit wrong here, it might be that your training doesn't get stable if you're not having a good or enough variability in there, and you're, for example, only optimizing always for the short and then for the long sentences. Good. Any more questions on this? Then we can go to the last part, and this is the update rule. So the most simple update rule is this. So we always take the same learning rate and like always change them based on the gradients, but the change is always like how much we change is always the same. So the step size we are going is always the same. This might be a good first step, but you can imagine this might not be always the best thing. So maybe at the beginning, it's better to go bigger steps and then later do smaller steps so that we really converge or something like that. So there is quite a lot of work in how to find good learning rates, because this is a very important hyperparameter, like how much do you want to go into the direction. Again, if you go into too few in the direction, you're not really learning something new. If you're going too far in the direction, you're jumping over the minima, and what you mainly do is some random guessing. So yeah, we have to find there a bit of a better way of doing it. And we'll try to do that on the example, get more and more complex algorithm now. There's a bit of math in that. The hope is don't get frustrated by the formulas now. It's mostly important to get the basic idea of that. So one thing you could do is more like a learning rate schedule. What that means is that you're saying exactly at the beginning we are going quite far, and then later we are doing only very small steps. So in the beginning you mainly have your n0, your eta zero, and you're doing eta zero is bigger. So you're doing like these big steps. And once you have done tau iterations, so k is your iteration, if tau times k is 1, then you're no longer doing n0, but you're doing n tau, which is like maybe 1% of your iteration. So at the beginning, you're doing large steps, then you're doing always less and less of these large steps, and you're putting more and more value to the second one and doing that. And that is a very, very simple thing of doing. So maybe there's more to do, and maybe it's especially the idea often is, can we learn something from what we have done before? So if we're doing always in the same direction, that means, oh, this seems to be good. Maybe we should go further in this direction. If we're going always in different direction, maybe it's not so good and we shouldn't go to that. So this is, the first idea, they call it momentum. So the idea is if the gradients go in the same direction always, that is good. Then we can go more and more in this direction. In contrast, if the gradients always go in different direction, then maybe we shouldn't do so big steps, because somehow anyway we're running only randomly around. So that introduces velocity in there. And what we're doing is you're doing the exponential decaying of the moving average. So you calculate a moving average, so the average of all the gradients, and always update by this gradient. But the average is not equally, but the last gradients are more important, and the longer ago the gradients are, the less important they are. So what you mainly do is here, you're taking your new velocity is your old one, but the old one is a bit decayed, so you don't take everything, but maybe, for example, 0.8 or 0.9 of the previous one. And then you're adding the new direction that you have. So this is the new direction of your update. So instead of what we had before, where we put this one to update our parameters, now we take also into account which type of update we had done before and add that to that. So that we're not, if we're going like crisscross, we're always going crisscross, but we are staying a bit more stable by averaging them. And in this case, you directly see the larger your value of alpha is, the more effect you put to the previous gradient and the less effect to the new gradient. what does that mean? That means the more, if you go often in the same direction, you're more and more updating that. So you can see that. So just assume your gradient is always really going into the same direction. What is happening? So first, your velocity here is normal if we initialize it with 0. So this is your normal update rule. You applied also here before. If now in the second step, I mean, this of course doesn't really happen. I mean, they will never be exactly the same thing, but just for understanding, assume you're always going in the same direction. So in the next step, you're not going, you're going there nearly twice in the direction. So you're going with nearly double speed in the same direction. So you have here 1.9 times the direction. In the next step, it's 2.71 times. So you're always speeding up, and then it's 3.44 and so on. So you're going more and more in the direction, and then your step size gets bigger and bigger. Because if you're always going in the same direction, the algorithm assumes, oh, this is a very good direction. So we can speed up the process and go faster into the right direction. This is a general thing we'll see, which comes up again several times in order to really speed up the process. You can do it also a bit different, and that is what is called the Nestrov momentum. And here we are not at the current point calculating the gradient and then doing our momentum term. Instead, we are going into the direction of the momentum. So what we previously said, we are calculating there the error and then adding that up and going again. So instead of calculating here at this point, we are already calculating, taking the step of the gradient. So based on what we had before, and then calculating the new error, updating it and going further. So how does it work? So you see, it's very similar. So this was a normal momentum term. So the new velocity is the alpha times the old velocity plus the loss. So with this one now, it's somehow the same way. The only difference is where we calculated our error, what we used as input or as weights. So here we looked our current neural network, so we calculated it here. While here, before we calculate do the backpropagation, we already update our network with the momentum term. So we are going here and then calculating there the type of error. So this is the only difference here. Which parameters do we do to calculate our loss? Do we take the current one, or do we first take a step in the direction of the momentum, then calculate, and then do the update? So you see that also here, there's a bit of difference. So we get our batch size. Then the first thing is we're updating it in the direction of the momentum. For the first time, it's easy. The momentum is 0, so it's the same, but afterwards it's done. Then we are calculating our sum. Then it's again the same thing. We're calculating our new velocity and updating them based on the velocity. So between momentum and the Nestrov momentum, the calculation of the velocity is the same. The only question is when we are doing a parameter update, and we're already applying here some type of update. Good. Any more questions to this type of momentum term? So where we try to always go further in the direction from which we were coming. Good. Then we can make things even a bit more complicated. Because until now, what we did is we treated somehow all features the same. So there wasn't like a difference between that you want to change some features faster and other features you don't want to do as fast. And that is good when everything is somehow the same. However, it's a challenge if you have more like error spaces like that, where like in some dimensions things are more square, like more out of the way, and in others they're narrow. So then it means also like if you have large gradients in one direction, you want to maybe have a lower like learning rate to not like have exploding things there. If in other directions the gradients are very small, it might be to have larger things to do that. So therefore, you want to have like dedicated learning rates for the different dimensions, so that if you don't change one dimension, it might be to have a bit of a higher learning rate there to still go there in some direction. And that is achieved by downscaling the ways by the squared root of the sum of all the squares. So you're downscaling very high values to not get exploded there. The nice thing is this is quite straightforward, and that is what is done in other grade. So you see we have one additional variable here, our r, which is a previous value. So you're summing things up. So are there large changes in there or not? And then you're just calculating the pointwise scalar. So you're taking for each dimension, you're calculating the square of the values in there. So this is then again a vector. It's not a single value. And then what you're doing as your update now is not that you're updating all the same, but you're scaling them down by the square root of this r. So if in the last there has been very large updates in there, then it might make sense to do less updates here. If there hasn't been, then you don't do that. That is, yeah, some of the next thing you add there. So you do this additional accumulation, which is in some way the second derivative then, and that allows you to like have dedicated updates for the different dimensions you have. There's one problem with this, and that is that this might be a bit too aggressively. So if you once have done large updates, you're not really changing, or if you have once had very large values in there, you're not doing any updates there anymore, but it's somehow staying fixed, which, yeah, might not be super helpful, because if you're then somewhere and there you only have small updates, you don't get out of that again. And that's why it might make sense, again, what we had before, not to take the whole over average over all the time, but to look only more, take the last updates into account. And if the last ones are small, we can do again larger steps. But if we before, like sometime very long ago, had already large, that shouldn't match it. So we can do the same thing we did before. So instead of, when we do the accumulation, instead of just taking our r plus, we modify them with some parameter. So beta times r, and the other one is the new weight is 1 minus beta. And you see the longer signs go away, you multiply them always with beta, which should be lower than 1. So they get smaller and smaller and smaller and smaller. And at some point, there's a very old values don't have really a good influence or an important influence. Good. So with this, we're nearly done, but not yet. I guess if you have trained a neural network, does anybody, which optimizer did you use?
Adam?
Yes, exactly. So we have to get to Adam. The nice thing is we have the basic things here. The only thing we have to still do is like combine all the things we had. So, or like one small additional thing. But the main thing is now, okay, we have on the one hand this from Aris prop, our accumulated momentum 2. Maybe it's good to also take the momentum 1. And you can combine both now that you not only calculated the R, but also you calculate the normal momentum, which we had done before. So you remember it was beta 1 times m. So there were plus the gradient we have now calculated. So that's exactly the momentum term we had before. And now the only difference, so we have to use this. So instead of here using the gradient in the update rule we had before, we are now taking the one which is averaged over the previous one. So then we have some of both in there. On the one hand, per direction, if we're always going into the direction, we're scaling lower. But in general, if you always go in the same direction, we're increasing things. So then we have both of them in there. That is what people refer to RMS prop plus momentum. And now there's only a very, very small step to add on. The only thing is that this term is a bit biased. The problem is that you initialize both the momentum and the second momentum with with the value 0, saying that, of course, at the beginning, you assume both of them are 0, which, of course, is not the true. And at the beginning, that therefore might not be very good. So what you're doing is you're unbiasing that by dividing them by something that depends on t, which is the iteration you're in there. That is all you do. Otherwise, you see, then you're using this. And this is then the Adam algorithm, which is, I would say, by now, the default thing you're always using, or which works at least decently. Interestingly, again, not only for one type of problems, but for very different types of problems. Good. So what you should remember here is we had these different types of algorithms, some using the first momentum, some using the second momentum, some do both. And then the Adam also has the bias correction. So in this way, you see, you can do, or you should do, adapt your update rule. And the challenge is that we have a non-convex problem. So just doing basic updates might not really lead to good performance. It really depends significantly on like what type of network you're having and so on. So this is really something where you often can lose more than like having the newest type of architecture. So what you should keep in mind from today is, on the one hand, what gradient descent is, how you do your training, and we looked at 3 different types of important points in there. On the one hand, the sample size, then on the stopping criteria, and finally on the update rule. And by combining all of them, you or using the right ways there, you can achieve a hopefully relatively stable training so that you get repetitively similar results in there. And any more questions? Good. Then I hope it wasn't too much math. Thanks for coming, and we'll see each other again next Tuesday here.